Hello everyone. My name is Jens Neureither and I'm part of a team from University of Darmstadt and University of Würzburg in Germany that created LegIoT, a ledger trust management platform for large-scale heterogeneous IoT networks. In the following 20 minutes, I'm going to guide you through important questions like what LegIoT is, why we built it, how we built it, and what we were able to achieve with our prototype. First, I'd like to start with a short motivation. It's needless to say that the Internet of Things gained more and more importance in our everyday lives. We're using smartphones, fitness trackers, we equip our houses and gardens with smart sensors, and we even equip our cars, traffic lights, and parking lots of supermarkets. And in the future, there will also be smart factories producing very customized products. And this is great, but at a certain point, there will be a trust problem because devices will ask themselves if they can trust the measurements of other devices, for example. And the larger these interconnections get, the harder it will be to establish a trust relationship between many of these devices. This leads us to three major challenges in building IoT trust relationships. The first challenge is that it is pretty hard to use unified schemes for trust establishment in such a scenario because we have a very large number of devices and a great heterogeneity. The second challenge is that the IoT devices deployed in such a network are usually mutually mistrusting. So they are not produced by the same manufacturer, and also the owners might be mistrusting. The third challenge is that whereas we can build and scale trust relationships very easily, for example, with a PKI, which is a central authority, it is not very good scalable for scenarios without a central authority. Next, I'd like to shortly dive into state of the art. In the context of trust establishment methods, there are two major areas. On the one hand, we have behavioral monitoring and anomaly detection, and on the other hand, we have stronger types of trust indicators. And this could, for example, be the usage of cryptographic keys or especially attestation evidence in the context of remote attestation. But these approaches have certain limitations. For example, behavioral monitoring is only able to detect infected and malicious devices when they deviate from the expected behavior. So if they play along the rules, then we will never see whether they are compromised or not. Cryptographic keys are cool, but they lose their benefits if the platform is compromised. So the attacker can just use these keys if they are not properly protected. And last, remote attestation is quite good for this scenario because it was actually developed for trust establishment. But we have the problem that remote attestation simply does not scale to large deployments without a central authority. So there have been some attempts like swarm attestation schemes, but they were not able to produce on-demand trust relationships. In the context of trust management schemes, we have recommendation-based schemes that are by their nature pretty well suited for decentralized systems. And the idea here is, like you might know, PGP, that we find someone who trusts a person we want to build trust into. And if we trust these persons in between, then we also are able to calculate some sort of trust score to the final person we want to trust in. But the limitation here is that we need the existence of intermediate trust links. So if we don't have someone who trusts this person, then we are not able to provide trust to arbitrary nodes. The second kind of trust management schemes are evidence-based, and they can, in contrast to the recommendation-based schemes, be used for trust establishment on demand. The problem here is that they typically rely on trusted third parties that deliver information about the state. So we can think about this as we pass the green guy some sort of test to figure out if he's trustworthy. But we need to correct this test, so we need to know what his trusted condition looks like, and this is usually delivered by a third party. Or we can use out-of-band channels for trustworthy information instead. But these are the limitations of evidence-based schemes. Next, I'd like to present you our contribution. The contribution of LegIoT is that we deliver a combination of evidence-based and recommendation-based approaches. So what I told you before, we were able to combine both of them through the usage of distributed ledger technology. Further, LegIoT is able to create on-demand trust establishment between mutually mistrusting devices. And this can also be, in contrast to, for example, PGP, without an intermediate trust link pre-existing. Further, we developed a novel graph enlargement algorithm, which is able to maximize the overall trust establishment performance of the whole system. And I'll show you later what this means. And as a last point, we contribute a trust management framework that can leverage various evidence-based methods for trust establishment. And this means that we do not rely on like one type of trust establishment method, but we can combine multiple which were not compatible before. Next, I'd like to present you LegIoT system model and design. In our system model, there are three major parties: the manufacturers on the left-hand side, the distributed ledger, and the owners with their devices on the right-hand side. The distributed ledger is a tamper-proof append-only data structure, which is collaboratively maintained in the network by different validators. The device manufacturers are trusted to produce a correct device in its initial condition. So the owners, while they are mutually mistrusting, trust the device manufacturers so that they receive a correct device. In the next step, the device manufacturer registers itself to the distributed ledger as a manufacturer. Afterwards, it also registers the different devices it produces and delivers additional information for them. Afterwards, the manufacturer actually produces the device and sells it to an owner. And this new owner is now able to deploy the device in a network of already existing devices, for example. Afterwards, it registers the newly deployed device to the distributed ledger. And at some point, some of the other devices might want to carry out a trust establishment to the newly deployed device. And after they have done so, they add a trust evidence to the distributed ledger. And now the task of the distributed ledger is to build a trust graph and refresh this trust graph every time a new evidence is added via a smart contract. So the question now is, why is this even possible to build a trust graph? And behind this, there is a concept of indirect trust we make use of. And I would like to show you the concept at this very simple example. So we have Alice, Bob, and Charlie is a baker. And now if Alice wants to trust in the quality of Charlie's bread, but she's never tried it, she asks Bob because she knows that Bob frequently buys at Charlie. And now it is possible to build an indirect trust relationship to Charlie. And we call this indirect functional trust to Charlie with a scope, where the scope is the quality of bread. And this is possible because Alice builds a direct referral trust relationship to Bob and listens to his recommendation. And Bob has a direct functional trust relationship to Charlie because the functional trust is that he can bake bread, and this is good. And referral trust is that Alice listens to Bob's recommendation. And when we combine those, we can gather indirect functional trust with a certain scope to Charlie. And there are like two criteria which must hold. For example, like the last arc needs to be direct functional trust, because if we don't have functional trust at the end of the chain, then we will never trust a function of someone. And the other criteria states that the scope can't be larger than the subscopes of the path. So what we do here is we take this concept of indirect trust relationships and we use it in our IoT device context. So we say that an edge is an evidence in the graph, a trust evidence, which was measured by a trust establishment process between a verifier and a prover. And the vertices are the actual IoT devices in the graph. And another point is that the trust scope, which I mentioned earlier, is dependent on the attested component. So if we attest the functional component of a device, then we get functional trust. And if we again attest the attestation component of another device, we gain referral trust to a prover. Further, we have two attributes that influence our edge weight. On the one hand, we have the static attestation method reliability, and it states whether we believe that some trust establishment process is very strong or it is not so strong. For example, we would say that a hardware-based attestation is always stronger than software-based attestation because it is key-based, for example. And the second attribute is the time-dependent edge deterioration. And we say, because this is a probabilistic approach, we say that by time the edges vanish because there is a deterioration in reliability. So if the measurement was long ago, then it is less likely to be still valid than a fresh one. And if we combine these to a path, we just multiply the different edges in a path. So we have the single edges consisting of attestation method reliability multiplied with edge deterioration, and then we multiply this again for the path. Next, I'll come to LegIoT operation. And if we have a verifier now, instead of directly making a trust establishment to the prover, it issues a trust query to our distributed ledger. And now the distributed ledger either returns a trust path and a path score, which is the best case, because in this case it figured out that there is already some sort of trust path existent from verifier to prover, and the ledger just says you can use this path and this is the current score. The other case is that there was no path found because no intermediate exists that makes such a path valid. And then the ledger will return some sort of entry point and a path score. So the path score is the score which will be reached if trust is built into the entry point. And then the verifier attests the entry point, which was named by the ledger, and submits this evidence again to the ledger, which includes it into the trust graph. And this way, there was a new path built from verifier to prover. Now, the next question is how these paths can be built efficiently. And here we can see that this is actually an optimization problem in the construction of a graph, because the challenge here is that we need to establish new edges in some way that minimizes the overhead for subsequent requests. And I'll show you what this means. And to solve this problem, we have the following parameters given. We have the network size n, so the number of participants in the network. We have the maximum number of hops, so we limit the path length. And we have the minimal reliability. So this is the reliability we assume for a path at a minimum. And last, we have the edge reliability function. And this is this edge deterioration function I introduced earlier. So here I will visualize how our algorithm works. So the initial situation is that we want to establish a trust link between the verifier and approver. And instead of doing an attestation directly now, we acknowledge that there is some sort of graph existing already. And now what we do is we expand the graph from the prover backwards. So you can see the yellow arrows here, which indicate what happens if we expand it. And now we see the blue nodes, and these blue nodes are all the nodes that could be used to enter the graph. And if we now choose the green node as an entry point, we get an indirect trust path from verifier to prover with the maximum distance of 4 hops. And what we see now is that all of the orange nodes are reachable indirectly from the verifier as well, because the entry point was connected to them. So in subsequent trust establishment processes, the verifier will also have trust paths to these other orange nodes. And this is what we achieve by putting the entry point as far as possible from the prover. Next, I'll show you some details to our implementation. Our LegIoT prototype consists on the distributed ledger on the right side, which is based on Hyperledger Sawtooth. And there are 3 transaction processors which were provided by Sawtooth, and 2 processors which we implemented ourselves. So the administration transaction processor handles like device registration or policy changes, while the trust transaction processor is therefore the actual trust queries of verifiers and the evidence submission after a trust establishment. On the left side here, you can see the clients. So we built our clients on a typical IoT platform, which offers a trust zone and is based on ARM Cortex-M. And it consists of 2 parts, the admin client and the IoT client, which communicate with the respective transaction processors. And to enable the communication, we have a middle box that translates the MQTT requests from the clients to HTTP requests, which the distributed ledger can interpret. Next, I'd like to dive in the evaluation of our prototype. In order to tell whether our system performs well or not, we define a central parameter which we call hit percentage. And this parameter divides the number of trust query hits, so the number where no additional attestation was needed, by the number of all trust queries, so all requests to the system. And therefore, we are able to vary the following parameters, which you already saw before. And we will do this in different simulations right now. First, we vary the maximum number of hops, so the path length, which limits our paths. And there we can see that we have some kind of horizontal asymptote, which these measurements approach. So at a certain length of the path, longer than 5 or 6 maybe, there won't be much of a benefit anymore because the path reliability stays slower anyway because we multiply the single edges on the path. But we can see that there is like a big impact compared between 1, 2, and 3 hops. And there definitely is a great benefit from longer paths. Next, the network size variation tells us what happens if we enlarge our network. And as you can see on this graph, generally the hit percentage decreases for higher number of nodes. But as you also can see, the maximum number of hops is able to counteract this hit percentage decrease. So for example, 6 to 9 maximum hops, the hit percentage is much higher for networks in size 800 to 1000 nodes. In the edge reliability function variation, we compare several functions that offer different characteristics in how fast they degrade over time. And therefore, we've chosen time intervals of like 60 to 120 seconds, for example, or 600 to 1200 seconds. And they also vary in the kind of how fast they degrade over time. And as you can see here, there is not much of a difference for longer trust chains of like 4 or 5 hops, but there is a difference for very short maximum number of hops, like 1 and 2 and 3 hops. Finally, I'd like to conclude our presentation with the following points. Our system has shown that it is able to largely reduce the number of attestations through the usage of the probabilistic approach I just presented. So just to keep that in mind, this is a reduction of up to factor 20 for a network of 400 nodes, which is quite a lot. We were able to provide a combination of multiple trust establishment methods of various architectures in a single system. So we don't need to bother anymore if these architectures are compatible with each other, but we can just include them in one single system. Further, we provide great flexibility because we don't need to attest whole groups anymore, like the swarm attestation schemes I mentioned at the beginning. Now we can build on-demand one-to-one trust relationships. And finally, security. Distributed ledger technology eliminates a single point of failure and enables trusted calculations which are also verifiable by other parties. Thank you very much for your attention. If you have any further questions or comments, please feel free to contact us because we are happy to discuss these points with you.